Okay, electric potential problem. Numero dos. That's 2. So what we're doing here is we're looking just for how much work is done in moving a proton, so that's a big kick right there for us, from a point of 125 volts to negative 55 volts, and we're doing this in both joules and electron volts. So let's just quickly draw some points for us here. Here's parallel plates. Doesn't really matter, they could be points, parallel plates, whatever. This is our 125 volts, and this over here is negative 55 volts. We know our electric field is going to be moving this way, at least through the plates. It's completely uniform. Edge effects. And all we were setting up to do here is say that the work is equal to negative Q delta V. Our Q here is a proton, so that is 1.6 times 10 to the negative 19 coulombs. And our delta V here is our final position, which is actually the negative 55. That's where we're going to wind up. And our initial position, the 125. So let's see. Negative 55 minus 125. That's going to give me negative 1.6 times 10 to the minus 19 coulombs times negative 180 volts. I get a wonderful negatives going away here, which is nice for us. And if we wanted to get this final answer in joules, we would just multiply these two numbers together, because coulombs times volts is joules, and when we do that, we get something around 2.88 times 10 to the minus, oh, let's see, that's 19, that's 1, 2, should be 17 here, to the minus 17 joules. Now, how would we get this in electron volts? Well, if we think about the word electron volts, the electron volt is by itself a great unit to think about. The electron volt having units of EVs is basically saying it has units of elementary charges times volts. That's what it's really saying. That is an electron volt. It's elementary charges times volts. Well, if this is a proton, this 1.6 times 10 to the minus 19 is an elementary charge. And how many volts we have? We have 180 volts. Yeah, and we got rid of the negative. So this right here in electron volts is just 180 electron volts. So we take the 180, we take the elementary charge, we take the voltage, and boom, that's it. 180 EVs. EVs are very, very nice to use. Because of this, it's kind of a self-defined unit. If we had some charge here that was like twice the charge of a proton, then instead of 180 EVs, we'd have 360 EVs. Ta-da! Because we just had twice the amount of charge there. So it's a very, very nice unit for us to work in, and it does imply, in that case, that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules, because that represents you having a charge Q of the electron volt, 1.6, and it's going through 1 volt. So the electron volt in and of itself is, if you take 1 elementary charge and you move it through 1 volt, what do you have afterwards? So very, very straightforward. Nice little problem there, very similar to E1, or the first example we did, and we just looked at electron volts in a little bit more detail there. So nothing too bad. With that, this problem is finished. Take it easy. Adios.